All right, well, I will start now. I want to first remind you of the logic of what we're doing as far as high energy effects. So there's a lot of unknown high energy effects. We really don't know what's going on there. The trick is that that's, by the uncertainty principle, that's effectively local. Everything that's effectively local looks like a term in the Lagrangian. And so that unknown high energy stuff ends up being in the renormalization of parameters. Renormalization of coupling constants or masses or etc. Okay, so basically anything that happens at high energy fits into that mode. It might be nice otherwise, but that's what it is. But that includes infinities. Okay, which is why they disappear in the end from the calculation. They end up ending up in these renormalized parameters. And so you have to then measure these. And you measure whatever the effect is afterwards. Okay? And so we just go through and do it. But there's a potential problem if you have a lot of things that are infinity and you're adding and subtracting infinities. So what we do, it's called regularization. Okay, regularization is an artificial way to make the loop integrals finite. And at least temporarily, you then can add and subtract them easily, so then you calculate away. And then you remove, at the end of the calculation, you undo whatever you did, and you get your answer is then undo regularization at the end. Okay. So that's the game. The methods, there are various methods. There are actually more than I'm going to tell you about here. But so let's make method number one. It's called Pauli-Villars. It basically is imposing a cutoff. Okay, so it's a technique for imposing a cutoff on the integral. So instead of being infinite, it goes up to some value. And here's how you do it. You take a propagator, 1 over p squared minus m squared, and you subtract off from that 1 over p squared minus lambda squared. And if lambda were infinity, then that's no change at all. You just set lambda to infinity and go away. But for finite, any big but finite lambda, the large p behavior of this cancels. So as p goes to infinity, this is softer. And that makes most calculations finite. Okay. So it's just basically a way of imposing a cutoff. If I rationalize that, that's 1 over p squared minus m squared, and then minus lambda squared over p squared minus lambda squared. Okay. Yeah, technically it's m squared minus lambda squared, but that's very small, so lambda goes to infinity at the end of the calculation. So that's one way to make these integrals finite. I'll do one of those with you. The advantage of this is it's relatively straightforward. The problems are it sometimes destroys some of the symmetries. Okay, and you can see that, for example, it causes trouble for gauge invariance. Okay, because gauge invariance we saw was connected with m of the photon is equal to 0. If you gave the photon a mass, you don't have gauge invariance. But if you do this trick with this propagator, so the first side will have m equals to 0, but the second side has m equals to lambda. So it's like subtracting off a photon with extremely large mass. And that causes troubles with gauge invariance then. So some of the things that happen normally with gauge invariance no longer happen. Okay. If you know anything about chiral symmetries, it's also associated with massless stuff. This also causes troubles there. You can get around this sometimes. I've done calculations where I've used cutoffs in E and M, and there are tricks to get around it, but you have to stand on your head. Okay, so that's the one that you especially find that in older books. The one that everyone uses is dimensional regularization. This takes, you take 4 dimensions and move it to d dimensions, and then d is thought to be then less than 4. And then if you have the integral dl over something, let's call it L squared minus M squared, when d is 4, this is log divergent. It goes like d4 L over L to the 4th, that's log divergent. But if d is less than 4, then it's finite. So it becomes finite. And in general, there's always a d. Well, it's not quite fair. There's most often a d where this makes sense. And then at the end of the calculation, you do the calculation in general d, and go to 4 at the end. Okay. We'll do that today. So this is good. This preserves gauge invariance. This preserves all the symmetries. Okay, and that's why it ends up being used. There. Yeah. Right. Yeah. Well, so again, the logic is that so that we can add and subtract them, we want to temporarily make them finite. Okay, and we'll have this parameter d goes to 4. And each of these you'll be able to see as d goes to 4, they diverge. So they're appropriately infinite when d is 4. But when d is not 4, they're not. And so, but then you add them all up, and your answer doesn't depend on d, or at least it's smooth as you go there. And so at the end of the calculation, you just let d goes to 4 at the end. Okay, so they were there to begin with, but not along the way. Okay. The only problem that you have here is gamma 5, which is gamma 0, gamma 1, gamma 2, gamma 3, seems to not have a good d-dimensional extension. So there's problems with gamma 5. And so there's a whole little literature that I'm not going to even go over, but you need to know that in case you start doing real calculations. Okay, so let's first do an integral in Pauli-Villars. Okay, and so what I'm going to do as my example is I'm going to do the integral that we've been playing with all along here, I of 0, which we subtracted off and everything was finite after we did that. But here's the thing that we didn't calculate. I of 0, which is, the integral that comes into a diagram like that, with 0 momentum flowing through it, is integral d4L over 2 pi to the 4th I over L squared minus m squared squared. Okay, so that's the basic definition of the integral. And for Pauli-Villars, we'll take this to go into integral. We stay in 4 dimensions, d4L over 2 pi to the 4th. And we then replace it's L squared minus m squared squared. Each propagator L squared minus lambda squared squared. Okay, so each propagator takes that identity up on top there. And we have 2 of them, and so that's the identity there. Okay. Now that's a nice finite integral, and we can do it, and I'll do it real quickly. If you watched that video where I showed you how to go through a loop integral, the first step is always Feynman parameterize. Okay. So that using that identity, the I of 0, well, there's a minus lambda to the 4th. There's 2 types of propagators, and it is the identity I gave you had a dz1, dz2, z1, z2, delta of 1 minus z1 minus z2 over it would be L squared minus z1 lambda squared minus z2 m squared to the 4th. And then we still have the integral d4L over 2 pi to the 4th. Okay. People want me to remind you of what that identity was? Or go through that a little bit more? Maybe I need to do that a little bit. The identity was 1 over a, b, c, dot, 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 is the integral d z1 dz2 dot, 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 delta of 1 minus z1 minus z2 minus dot, 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 all these z's. It becomes then a, let's make it a to the end at the end just so I know how many I got. A z1 plus b z2 plus dot 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 up to a n zn to the nth power. Okay, and that's just a simplification of this. And then if you want to, if you have 1 over a squared b c dot dot dot, you differentiate this with respect to a, and it turns into dz1 z1, then dz2, etc. delta a z1 plus the same old stuff to the n plus 1. And there must be well, there must be an n there. I've missed something. So this is n minus 1 factorial. That's n factorial. Okay. Okay. So first step is always Feynman parameterize. The second step is Wick rotate. Okay. The trouble with the integral up above there is we have L squared, which is L0 squared minus L vector squared. And we really didn't like having that, so we take advantage of some complex analysis to change the integral that's over the real axis into one that flows over the imaginary axis. Yes, I'm doing this quickly, partially because I had it in notes previously. But then the identification here is L0 is be sure, IL4, yes, L4, so that this turns into minus L4 squared plus L vector squared, which is then symmetric. So if you Wick rotate this integral I of 0, turns into minus I lambda to the 4th integral d z z1 minus z. Okay, what I've done at that step here is in this Feynman parameterization, I do the integral over z2, so it becomes z, and z2 is 1 minus z1. So I just dropped the index there. Okay, and I still have the integral d4 L Euclidean over 2 pi to the 4th, 1 over L Euclidean squared plus lambda squared z plus m squared 1 minus z. Okay. And now I do 4D spherical coordinates. You're free to ask if you want me to say anything more about these guys. But now that's 4D spherical, symmetric. So everything here I do in 4D. So I write the integral d4L Euclidean as the integral L squared L cubed dl d omega in 4D. Okay, it's actually a 3 sphere in there. As I pointed out, and I'll actually do this one for you again, in 4D that's 2 pi squared. I'll do this for you in general D dimensions in a minute. And so my integral now becomes is minus I lambda to the fourth 2 pi squared over 2 pi to the fourth integral dz z 1 minus z integral d4L dl 1 over L squared plus lambda squared z plus m squared 1 minus z. And I should have written this up here to the fourth power, so watch that. I made a correction while you were looking at your paper there, right up here, and that's there. Okay, now you can, now it's an integral you can do, and maybe I don't need to do anything more. You know, you might, the only thing I want to just in general, these are integrals. Clearly you can do, you actually do have to keep this m squared here. You'd think, well, lambda is enormous. We're going to take it to infinity later. And so I could drop m squared compared to it. But there's a little corner of parameter space down here when z is equal to 0. As z goes to 0, m becomes important. And so you can't actually drop it here. And this is crazy stuff here. Let's correct that. Okay, anyone? That should just be L cubed. I have to correct that. So L cubed dl. Okay, so that's just simple integrals. Everyone can do those integrals. And I'll just give you the answer then. This turns into minus I over 96 pi squared log lambda squared over m squared minus 2. So you do this integral in general, and then you take lambda very large. So as lambda is large, that's what it goes to. Okay. Again, so here's where the m came. It came the fact that if you had dropped it, you'd be in trouble because your z integration would have been a problem. So it appears at the lower endpoint there, and that's it goes into the normalization of the log, which is fine. The other thing to comment on just on general grounds is you can't really drop the 2 here either. You know, you might say I can drop the 2 compared to log lambda squared because that's very big. But in this case you could. In this case it wouldn't have made any difference because I of 0 as a whole dropped out of the problem. But in some other case, if you have lots and lots of different divergent integrals and you're adding them all together, you have to keep the 2 because the other one might come out log lambda squared minus 1. And you add the 2 together, the log lambdas cancel, you know, so there's a minus sign, they cancel, and you're left over with the 1. So you always keep the finite piece, but you drop 1 over lambda squareds because those will never contribute. Okay, so that's doing it an integral by Pauli-Villars regularization. Let me do a more difficult one and more interesting one dimensionally. Okay, so again, the idea is we're going to take 4 dimensions and make it into d dimensions, presumably a d that where the answer is calculable and finite, and then at the end we end up taking d back to 4. Okay, so here I'm going to do the full integral. I'm going to do I of p. It's the same integral that we're doing in this type of problem here, where this is the momentum L, and here's L plus P. Actually, I'll make it L minus P. So one side has loop momentum L, the other side is L minus P. So the full integral, if you look at it, it was d4 L 2 pi to the 4th 1 over L squared minus M squared plus I epsilon 1 over L minus P squared minus M squared plus I epsilon. Okay, so that's the integral that we had to do before. We'll do it here. We'll make this integral dl over 2 pi to the d. This part will stay the same, L squared minus M squared plus I epsilon 1 over L minus P squared minus M squared plus I epsilon. Okay. Now, one of the things the obvious one, we took d4L into d sub L. It's conventional to do 2 pi to the d. That also that gives no contribution at the end of the day, but that's what people do. The other thing they do, and this is more interesting, is since the original integral is dimensionless. Okay, so here this integral is completely dimensionless. They stick a factor, mu to the 4 minus d out in front, where mu is arbitrary, but has dimensions of mass. Mass or momentum. Okay? Now, this then this now is still dimensionless. Okay, so L carries dimensions of mass, but so now it's only mass to the d here. This gives you a mass to the 4 minus d. It adds up to mass to the 4, cancels the mass to the 4 that's down there. So it keeps the dimensions the same. Mu had better also disappear. It's arbitrary. It had better disappear at the end of the day. But it's good for a couple things. By keeping the dimensions correct, your results are going to have dimensionless numbers in it. So in this case, there's an m here. There will be various factors of m over mu that are a dimensionless number. Those actually get exploited in a lot of field theory techniques. The fact that mu follows m or carries this 4 minus d. There's a lot of techniques that have grown up that follow that. Okay. Okay, so let's do this guy now. Here we have to do this one. There's a bunch of various interesting pieces of math here. Okay, so first I Feynman parameterize again. Okay. So this I of P then, it's actually simpler. There's only two propagators there. It's actually, this part's easier. I have mu to the 4 minus d, integral d to the dl, 2 pi to the d. I only need one factor, dz. Let me write out the answer and then we'll see it. I get L squared minus, L minus P squared minus M squared times Z plus L squared minus P squared, L squared minus M squared times 1 minus Z. And this thing raised to the square power down. And there's a plus I epsilon if we want to keep it. Okay? So, in my previous identity, I had a Z1 and a Z2 and a delta function of 1 minus Z1 minus Z2. I've just gotten rid of the Z2 and the delta function. So I just have dz, Z, that would have been Z1, and this would have been Z2, 1 minus Z. This integral runs from 0 to 1, and that's that. Okay. People okay with that? This can actually be simplified. It's the L squared piece comes with Z plus 1 minus Z. The M squared piece comes with Z times 1 minus Z. So those are the same. So it's L squared minus 2L dot P Z plus P squared Z minus M squared with a factor of 1. Okay. So that's that. Now, the next step, we didn't have to do it before, but here we have to do it. We have to shift the variables. So let me define K is L minus PZ, so that K squared is L squared minus 2L dot PZ plus P squared Z squared. Okay, so if I've defined that, then this first term here is that first term here, and all I have to do is correct for this. So I'll write the denominator. The denominator goes to then K squared, takes the first two terms there, plus P Z 1 minus Z, that's P squared, plus minus M squared. Okay, so K squared has a plus P squared Z squared. I changed, I cancel that by having a P squared Z squared with a minus sign. So this expression is the same as that one. Okay. Now I will define this as K squared minus A squared. And I guess I'll keep the plus I epsilon there. Okay. Then next step is always this wick rotate. I take L0 and write it as IL4, or in this case it's K0, K4. So the integral becomes I mu to the 4 minus d integral dx integral d k Euclidean over 2 pi to the 4th 1 over k squared plus a squared minus I epsilon squared. Okay, so all those things have nothing to do with d dimensions, and that was 2 pi to the d. Okay, so that has nothing to do with d dimensions. Now comes the fun part. Okay, I have to do a d-dimensional integral where d will be in the end treated like a continuous variable. So how do you do a 0.1 dimensional integral? Okay. Well, here's a good case. I'm going to do the angular integrals. Okay. I'm going to do the angular integrals in d dimensions, and we'll think of d being integer to start with, and then we'll get the final answer and let d be anything. Okay, so let's do the angles. So clearly when we're doing this integral, this is at this stage spherically symmetric. So we'll write that as k to the d minus 1 dk. That's always there. That's the usual stuff. And then there'll be a little d omega appropriate for d dimensions. Okay. Now, okay, well, how do you do the k to the d minus 1 is easy to let that be fractional dimensions, but how do you do an integral over a fractional number of angles? Okay, well, let's do it. The integral over d omega sub d is, well, just think of how it starts out. It starts out typically d phi from 0 to 2 pi. That's true. You know that in a circle, so if it's a two-dimensional one, that it stops there. If it's 3 dimensions, you have to then do also an integral over sine theta d theta. This goes from 0 to pi. Okay. Since we've got a few more to do, I'll call that theta 1. And the generalization to higher dimensions goes as follows. It just keeps going. It goes sine squared, and the next one is sine squared theta 2, 0 to pi. And it just keeps going up. And the last one is sine to the d minus 2 theta d minus 2 d theta d minus 2. Okay, you get the top power by well, you know where to stop. If we were in 3 dimensions, we're doing the appropriate angles for 3 dimensions, you want to stop at sine theta d theta, so you want it to stop with just one sine theta, so this goes to d minus 2. Okay. Fair enough? Well, now we have to do this. Now, at this stage, d is an integer mentally. So let me do the last one first. The last one, I'll give you the way we write this in terms of gamma functions. I'll give you a quick gamma function review in just a minute. This, in general, for general d, is d minus 1 over 2 divided by gamma of d over 2 times pi to the 1/2. Okay, so that's I'll do the gamma function review in a minute. So just take it. This is the gamma function. Okay, and that integral, in fact, this is a general expression true in any dimensions, but we're now thinking of it being integer. So let's do that. And we come down here. We've got a lot of stuff in between here. This guy becomes gamma. Oh, what is it? So let's see. D. That would be like gamma of 4. So 4 minus 1 is 3. So it's gamma of 3/2 over gamma of 4/2. This one is gamma. So it's like d is equal to 3. D minus 1 is 2. So gamma of 1 over gamma of 3/2. This guy is then gamma of 1/2 over gamma of 1, except there's a factor of 2 out in front, because the last integral runs up to 2 pi. So, and these all have pi to the 1/2. Okay, so the answer turns into 2 pi to the d over 2 over gamma to the d over 2. Okay. So that's really the claim. So this being done for integers is fine, but now this one can be used for any d, including fractional ones. Okay, so once you've done that, okay, so this is always fun. I don't know if you find it fun, but that's what dimensional regularization does. Let me do my little gamma function review. Okay, so the gamma function gamma of z has various definitions, but the one that is most commonly cited this is a famous Euler integral. But more to the point, for you the properties are interesting. Gamma of 1 is 1. Gamma of n is, well, gamma, let's do gamma of z is z minus 1 gamma of z minus 1. So that's an identity. That's the crucial identity actually for the gamma functions. This then says that gamma of n is n minus 1 factorial, because you can just keep reducing it. Gamma of 3 would be 2 times gamma of 2, which is then 1 times gamma of 1, so it becomes n minus 1 factorial. And gamma of 1/2 is square root of pi. And for us later on, let's also just do it here. So gamma of minus n, so any negative number, negative integer is infinity. Gamma of 0 is infinity. But gamma of epsilon, okay, so now epsilon is small. Okay, so epsilon is going to be going to 0. Okay, is 1 over epsilon minus a different gamma. And that lowercase gamma is the Euler number, which is gamma is the limit m goes to infinity of the sum 1 plus 1 over 2 plus 1 over 3 plus 1 over m minus log m. So it's, you know, that sum approximates log m. And as a number, it's 0.577. All this wonderful math identities there. Okay, so there's your gamma function. So let me actually just do some checks for you. Make sure that these integrals are right. In 2D, d is equal to 2. Okay. Then we have their gamma of d over 2, which is then 1, is 1, implies integral d omega in 2 dimensions is 2 times pi. Okay. So that works. In 3 dimensions, we have gamma of 3/2, which is then 1/2 gamma of 1/2, using the crucial identity here, which is then 1/2 times square root of pi. And so then we end up with integral d omega in 3 dimensions is 2 pi to the 3 over 2 divided by 1/2 square root of pi, which is, sure enough, it's 4 pi. And for d is equal to 4, gamma of 2 is just equal to 1, again by the n minus 1 factorial, and implies that integral d omega in 4d is 2 pi squared. Okay, good. So that was our toughest integral. If you can survive that, you'll survive dimensional regularization. Okay. So now all we have to do, so we've got, let's copy it over, I of p is there was a factor of I mu to the 4 minus d integral dx. We just did a factor of 2 pi to the d over 2 divided by gamma of d over 2. We have a 1 over 2 pi to the d, 2 pi to the d, and we have left over then integral dk k to the d minus 1 over k squared plus a squared is a minus I epsilon, but we don't need it. Yeah, maybe we should carry it along. Squared. Okay, so that's then an easier integral to do. This integral runs from 0 to infinity, and we pull out one more fancy identity. If gamma of x, gamma of y over gamma of x plus y. There we go. That's the integral 0 to infinity dt t to the 2x minus 1 over t squared plus 1 x plus y. Okay, so there's this famous fancy identity. We're going to apply this with then x is d over 2, right? Because 2x minus 1 is then d minus 1. X plus y is equal to 2, because that's what sits downstairs there. So that y is 2 minus d over 2 is then 4 minus d over 2. Okay, so by this identity, we have gamma of d over 2, gamma of 4 minus d over 2 divided by gamma of x plus y, which is 2, that's equal to 1. So the downstairs gamma is just unity. The gamma of d over 2 cancels that gamma of d over 2. And we're left over with gamma of 4 minus d over 2 plus stuff. Okay, so then all right. So I of P is actually maybe one other thing I should say before I do that. This expression here has t squared plus 1. This has k squared plus a squared. So basically, I have to do a change of variable. There's a to say that t is k squared divided by a squared, such that this becomes t squared plus 1, and then I have to factor out powers of a. You'll see those in the final answer. Okay, so let's write it out. There's I mu to the 4 minus d. There's 2 pi. No. Okay. The numbers, just let me collect them up. It's 16 pi squared times 4 pi to the d minus 4 over 2. So we can take a look at that if you want. There's the important piece is the gamma of 4 minus d over 2. And then I have the integral dx 1 over a to the 4 minus d over 2. Okay, remember a was m squared minus p squared x 1 minus x, so that carries the x dependence. All right, unless you insist, you can just trust me on these numerical factors. This one just comes from this change of variables here, the a to the 4 minus d over 2. And you could see that that's about right, because when d was equal to 4, this was dimensionless, and so you could just change variables and get rid of everything. Okay, so 4 minus d over 2 is about right. But the interesting guy is this guy right here. There's the one that says that if I was doing this in 3 dimensions, this would be nice and finite. But in 4 dimensions, that becomes gamma of 0, and gamma of 0 is infinity. So that's our divergence. Okay. So can we just set, we can't at this stage set it equal to 0, so we do the following. We're going to define epsilon. It's now a different epsilon, but we always use epsilon for small numbers. 4 minus d over 2. Gamma of epsilon is then 1 over epsilon minus this Euler number, 0.57. And I've got a bunch of other 4 minus d's over 2 floating around here. Okay, so how do you, the temptation is just say, well, out here, this is mu to the 4 minus d, that's mu to the epsilon, mu squared to the epsilon. So I just set d is equal to 4 on that, and that's finite. But it's not quite fair, because we have this 1 over epsilon from the divergence there. So we use the following identity also. So it's if you have some number a to the epsilon, you write that as e to the epsilon log a. Okay, that's an identity. Is 1 plus epsilon log a, dropping epsilon squared. And then when you have then 1 over epsilon e a to the epsilon, that's 1 over epsilon plus log a. If anywhere you see 1 over epsilon, some number to the epsilon, you pick up a finite factor of log a. Okay? So here's then the integral. I of p is I over 16 pi squared 1 over epsilon minus gamma, that's that factor. And then various things are, it's integral dx. I have 1 plus epsilon log mu squared minus epsilon log a minus epsilon log 4 pi. Okay, and so this ends up being I over 16 pi squared, 1 over epsilon minus gamma minus log 4 pi. And let me write it as plus log mu squared over m squared, and then plus the integral dx log m squared over m squared minus p squared x 1 minus x. Okay. Good. Now we're done. So here's, you can sort of see the way I've written it here. This is what I've previously called delta I of p, which is I of p minus I of 0, because this vanishes when p goes to 0. So as p goes to 0, this vanishes. And likewise, this guy out here is I of 0. There's my I of 0. And that's the divergent piece that in the end drops out. This was just the same as calculated before. It isn't obvious, but if you do enough integration by parts, you can put it in that form. And there I'm done. Okay, so if once you do that log integral, it's a regular integral now, you're done. Okay. So a couple things you can see here. You can see that we're in I of 0, well, previously we had log lambda, that turns into 1 over epsilon. So divergence is, it looks like 1 over epsilon. When you can see here also when 1 over epsilon disappears, the log mu will disappear, and also this log 4 pi. Okay, and that's just the effect that physics is independent of mu. Okay. Yeah, I guess that's all I really need to do at this for this guy. All right. Actually, that went a little slower than I probably would have liked, but we had a bit of review along the way because I wasn't convinced that everyone's remembering some of the tricks. But that's how you do dimensional regularization. Okay, this pattern gets followed. That whole pattern gets followed. There's often these are tabulated. So if you look in the back of our book on the standard model, you see many of these integrals tabulated. But very often not the one that you want. So you actually have to do this a lot at the time. Okay, let me stop there. We come back to the last renormalization issue is going to be talking about mass and wave function renormalization. We'll tie it all together and get out of renormalization. Okay? Good. See you next time.